Hey guys, today we're going to talk about electrical potential, and then the next set of videos I'll post some work examples uh, from the book. We're probably not going to do a whole lot of really complicated homework problems from this chapter, um, but I do want to spend some time really stressing the idea of a potential and the relationship between potentials and fields, because this is actually really, really important stuff. So the book actually starts out by referencing all the way back to chapter 8 when we talk about potential energy in the context of gravitational forces. If we think about, refresh our memories, what gravitational potential energy is, remember we defined gravitational potential energy as PE. Well, actually, we can use PE in this course. We use U, the more technical uh, textbooks refer to potential energy as U, and that's equal to mgh. So as I take an object and I lift it up in the air, uh, I increase its potential energy. So since the force that gravity exerts on something is equal to mg, when you lift something, the force that you exert on it has to be equal to mg to lift it at a constant velocity, and this height, delta h, the higher you lift it, the more potential energy it has. This is the force you exert, and this is the distance over which you exert that force. And the expression that relates force and work is that the force dotted with the distance, if the force is constant, is equal to the work done. So the work done when you lift a object, a height h, is equal to the change in potential energy. The work you do is positive. When you lift an object up in the air, you do positive work. The work that the force of gravity does when you lift an object up in the air is negative. You lift up while gravity is pulling down. So the work done by the force of gravity is equal to negative mgh. And that's important. So when you increase something's potential energy in a force field by lifting it up against the field, you do positive work, but the field, the force that you're working against, does negative work. How does this relate to well, before we relate it to electricity, let's look at a slightly more general expression. If the force that you're working against is not constant, you can't just multiply the force times the distance, then the work done, say, by the force of gravity when you lift it up against that potential is equal to the integral of F dot dl. So the change in potential energy of the object is equal to the negative of the work done by gravity, which is equal to the negative of the integral of F dot dl. We can write that then if the force, change the highlighter here, if the force is equal to the negative, the potential energy change is equal to the negative integral of the force, that means the relationship between force and potential energy is that of a derivative. So we can write that the force on an object in a gravitational field is equal to the negative derivative of the potential energy with respect to position in the case of a gravitational field. And you've got an object in a gravitational field that has potential energy equal to mgy, where y is the vertical coordinate. So the force on this object is equal to, is that behind my head? Not yet. Okay, equal to negative du dy, which is equal to negative mg, which we should recognize is just the weight, the force being exerted by gravity. So this relationship between the potential energy and the force is universal. It goes for any conservative force, and electrical forces happen to be conservative forces as well. So what your book does next, this is in the beginning of chapter 23, is write an expression for the work done moving a force through an electric field. If we imagine an electric field that's constant, for example, and I didn't put the diagram in here, but we imagine an electric field that, say, to the electric field of an infinite line or an infinite plate, the electric field is just constant. What was it? Sigma over 2 epsilon naught, I think, for an infinite plane of charge. So if we move a charge from one point in that field to another, there's going to be a change in the potential energy. And the work done is simply the force times the distance. And since the force on an object in an electric field is just Q times E, force is Q times E, then the work done moving an object through that electric field is going to be equal to Q times E times the distance, how far you move it. And the change in potential energy is going to be the negative of that work done, which is going to be the charge times the electric field times the distance. Analogous to MGH, right? If Q is playing the role of the mass, the electric field is playing the role of the gravitational field, or what we call G in mechanics, and D is playing the role of how far you move that object through the electric field. So this is exactly analogous to MGH for a gravitational field. It's useful in electromagnetism to define a quantity that's not the potential energy of a particle, but the potential energy per unit charge of a particle in a field. Remember what electric field is defined as. Electric field in electromagnetism is defined as the force per unit charge, right? Find a place to write that. That the force on an object or a charge in a electric field is equal to Q times E, which means we can think of the electric field as being the force per unit charge. It is useful to define something called the electric potential, which is the potential energy per unit charge. So we use the symbol V for not potential energy, but electric potential. And the units of electric potential are volts. Volt. And it's a little bit confusing because this is one of those situations where the unit that we use to measure the thing and the thing itself are the same, so sometimes confusing about what we're talking about, units or the physical quantity. But we define this thing called the electrical potential as the potential energy per unit charge in an electric field, which means that the potential difference between 2 points in a field is equal to the potential at point A minus the potential at point B, which is equal to the work done, actually the negative of the work done, per unit charge, when you move an electrical charge through a field. Something to notice about the electric potential is that potential energy is a scalar, and electrical potential is just potential energy per unit charge. So it is also a scalar. The fact that potential is a scalar is one of the reasons that it's a useful quantity in electricity and magnetism. We're usually dealing with fields, and fields are vectors. We've seen that when you're trying to add up vectors, for example, you have to take care of the components or take the components into account. You don't have to do that for potentials because potentials are not vectors, they are scalars. So we'll see later on in this chapter why that is useful. So we want to be really clear about the relationship between force, energy, fields, and potentials. The relationship between a force and a potential is that a force is equal to the negative derivative of a potential with respect to position. This is in one dimension. If you've got a potential in 3 dimensions, this expression is more complicated. In fact, for those of you who have taken or are taking Calc 3, it is worth knowing that the force is equal to the negative gradient of the potential as a function of position in three-dimensional space. If you haven't taken Calc 3 yet, or have not seen this upside triangle gradient symbol, you just think of a gradient as a kind of three-dimensional derivative. So the force is equal to the gradient of a potential function, or the potential energy, function, which could be changing in complicated ways in three-dimensional space. You'll also see this sometimes written in some textbooks as the gradient grad u, where u is a function of position. If you've taken Calc 3, you know that the gradient function turns a scalar function in three dimensions into a vector function in three dimensions. So force is a vector, potential energy is a scalar. We also know that for an electric field, the relationship is that the force on an electric field, a force on an electric charge is equal to the charge times the electric field strength. That means we can write, if this statement is true, then Q times F. Well, no, let's not do it that way. How do we want to do this? Let's write it like this. Let's divide both sides of this expression by Q. So if the force is equal to dq dx, that means F over Q, force per unit charge, equals, let's go ahead and write it like this, 1 over Q times negative du dx, which is equal to negative ddx of potential energy divided by Q, and we have defined potential energy per unit charge as potential. So if this is the electric field, we can write that the electric field is equal to, at least in one dimension, negative spatial derivative of the potential. And the potential can be a function of x in one dimension, so this should be ddx. Write that more clearly. Force equals negative ddx of the potential. If we're in one dimension, if we're in three dimensions, we write this that the electric field is equal to the negative gradient of, parentheses, the negative gradient of the potential, which is a function of position in three-dimensional space. Okay. Sometimes you'll see gradient written with a vector symbol over top of it to denote that it is a function that turns a scalar field into a vector field. So what we have here is a relationship between the electric field and a potential in space, a scalar function in space that describes the potential energy per unit charge of objects placed into that field. And the electric field is equal to the spatial derivative, the rate of change or the gradient of that potential function from point to point in space. Okay. If we flip this relationship around, we can write that the potential difference between 2 points, A and B, if you've got a field in space, and you've got 2 points, A and B, then the difference in potential between those 2 points is equal to the integral, so delta V from A to B is equal to the integral from A to B of E dot dl, the integral through space. It's sometimes called a line integral. In fact, you'll sometimes see this written like that. of E dot dl from A to B, the negative sign denoting that we're talking about when we work with the field, where the field is doing negative work, we are doing positive work. So we just have to be careful of that negative sign. A reminder of what we mean by conservative forces. If a force is conservative, that means if you integrate this integral through space on some kind of closed path that comes back to A, the change in potential from A to A over any closed path of E dot dl has to be 0. The potential only depends on position. So if you come back to the same point in space after integrating this potential function in some complicated way through space, when you get back to the place you started, you've done a net 0 work. This is true for conservative forces, and the electric field definitely is a conservative force. Some examples of things that aren't conservative forces are things like air resistance and friction, that the amount of work done depends on the path taken. That's another important thing to remember about conservative forces. If you've got some field E in space that might vary from point to point in a complicated way, and you've got 2 points A and B, A and B, that this integral does not depend and cannot depend on the path that you take going from A to B. So if you integrate E dot dl over this path, you integrate E dot dl over that path, the change in potential has to be the same because the potential only depends on position. So the work done in going from point A to point B cannot depend on the path taken. Again, that is one of the things that distinguishes conservative forces from non-conservative forces. So how do we use this to actually calculate things? Your book in section 23.3 derives an expression for the electrical potential due to a point charge with charge Q. And it's very straightforward if you know that the electric field of a point charge is just given by 1 over 4 pi epsilon naught Q over R squared. And you know that the relationship between potential difference and the field is that you can think of it either way, that the potential is equal to the integral of the field from one point to another, or the electric field is equal to the negative derivative of the potential through space. If E is 1 over 4 pi epsilon naught Q over R squared, and the potential difference between 2 points is just equal to the integral of E from one point to another, we know that because of symmetry, none of these things can depend on, if you've just got a point in space, everything can only depend on R. So this integral E dot dl just becomes the integral of E, Q over 4 pi epsilon naught, 1 over R squared dr. And the integral of 1 over R squared dr is just negative 1 over R. So that negative, gets rid of that negative from the integral. And we have that the difference in potential between 2 points A and B at locations RA, RB is 1 over 4 pi epsilon naught Q over RB minus Q over RA. It's important to always keep in mind that only differences in potential and potential energy have meaning. When we talk about a difference in potential energy, remember we talked about this when we talked about just gravitational potential energy. I talk about lifting a rock up in the air and ask how much potential energy it has. You can talk about how much energy it has relative to the table or the floor or the ground outside if you're on the 3rd floor. All that's measurable, all that is meaningful are differences in potential, which means we have to make a choice when talking about electric fields. Usually when talking about a constant potential like gravity, you can just say, oh, the ground is 0 potential, and we measure potentials up from that. The convention for electrical charges, actually, let me go back, is because we want to set one of these potentials equal to 0. The place we choose to set the potential equal to 0 is at r equals infinity. And that is a choice of a 0 potential that is maybe a little strange, but it makes sense if you look at the shape of this potential for a point charge. If we graph the potential as a function of distance, it's proportional to 1 over r, right? Which means that if we're to make a graph of v versus r, at r equals 0, this goes to infinity, and it drops like that. So it makes sense to set v equal to 0 at r equals infinity, so that when two objects are far apart, they have less and less and less potential. If you think about two positive charges, the closer you bring them to one another, the more potential they have, the more they'll want to push each other apart. And this actually leads to another important thing, just thinking about graphs of potential in general, is that you can think of them as sort of pictures of a little roller coaster, and that shape of that roller coaster tells you what an object will do. If you put a positive charge in space near another positive charge, it will roll away and roll out to infinity. The force never quite goes to 0. It just gets smaller and smaller and smaller as the objects get further and further and further apart. If you've got a positive and a negative charge, you put them in space, the potential of, if you put a negative charge on this roller coaster, it will roll that way down the hill to approach the positive charge, and their force between them gets bigger and bigger and bigger and bigger as r approaches 0. So this relationship between a potential and a force, or a field and a potential, is one of a derivative, right? The electric field is equal to minus dV dx, or the force is equal to minus du dx. So the direction of the force is the rate of change of that potential in space. Okay, so what we will do in the next set of videos is look at some problems to determine the potential at a point in space, or the potential difference between 2 points in space, by integrating over the contributions of that potential due to little bits of electrical charge. And you will find that these problems look very, very simple. Here's example 8 and example 9 from the chapter. Actually look exactly like the two of the problems that we did back in chapter 21, finding the potential due to a ring of charge and finding the potential due to a disk of charge. One difference between finding the potential and finding the electric field is that potential is a scalar, so we do not have to worry about vector components when finding the potential at some region in space, and we'll find that makes these problems actually a little bit easier than electric field problems. So we'll do a couple of examples of that. I'll assign a couple of homework problems, and then we will quickly move out of chapter 23 and on to chapter 24 and 25 next week.